Thermodynamics. This is your tutor Pragya Sahu, PMRF scholar at Department of Chemistry, IT Kanpur. So in last class, we studied the molar heat capacities, and then we studied what are molar heat capacities at constant volume and at constant pressure. After that, we derived a relationship between them. Today, we will read how we can measure delta U, that is change in internal energy, and delta H, that is change in enthalpy of a reaction using calorimetry. Okay, so if you want to measure energy changes associated with a chemical or physical process by any experimental technique, then that technique is known as the calorimetry technique. Okay, so in calorimetry, what we do, the process is carried out in a vessel, and that vessel is called as a calorimeter. Okay, if we take a vessel and we call it calorimeter. Okay, so the vessel is called as calorimeter, and this calorimeter is then immersed in a known volume of liquid. Okay, let's say we immerse this vessel. Let's say this is your vessel. Okay, and then you immerse this vessel in a known volume of a liquid. Okay, this is your vessel. Okay, and this is your liquid. Okay, suppose water is filled over here, then you have immersed this vessel into this liquid. Okay, and if you know the heat capacity of this liquid and the heat capacity of this your calorimeter, then you can calculate. Okay, so in order to calculate the changes in energy, then if we know the heat capacity of this liquid and the heat capacity of this calorimeter, we can easily calculate. Okay? So here it is written that calorimeter is used for measuring the amount of heat change. Okay, if we want to measure the amount of the heat change occurring during a reaction, okay, occurring during a physical or chemical change, then we will use calorimeter. Okay, so in calorimetry, what happens? The temperature change in the process is measured. Okay, so what we basically measured in this process is the change in temperature, and this change in temperature is directly proportional to this change in temperature is directly proportional to the heat capacity. This change in temperature is directly proportional to heat capacity. Okay, so we have already know this expression that your Q was equal to M into C into delta of T. Okay, if you want to see this equation, then in this class, I have told you that if Q is your heat, then it is directly proportional to the change in temperature and mass. Okay, and if we remove this proportionality constant, we get this C, and which is nothing but the heat capacity. So if we arrange this equation, we will get C, which is heat capacity, is equal to Q by M into delta T. Okay, so this was the expression. So C is, if we arrange this equation, we will get C is equal to Q by M into delta of T, which is written over here. Okay, this equation is coming from that. Okay, so if we use this equation, okay, then we can calculate the amount of heat change in the process. Okay, if we okay, see in this process, what we actually measure is the temperature difference. Okay, so if you know the temperature difference, that is delta T, then you can easily calculate this C, heat capacity. Okay, and if you know this, you can easily calculate your delta U and delta H value. So now, so calorimetric measurements are made under two different conditions. Okay, so these measurements are done under two different conditions. If we do it at constant volume, then it will be QV, which is nothing but your change in internal energy delta U. And if it is at constant pressure, that is QP, nothing but delta S, that is change in enthalpy. So let us first study the measurement of delta U, that is change in internal energy. For a chemical reaction, heat evolved at constant volume, which is nothing but your delta U, is measured in a warm calorimeter. So for the measurement of delta U, we use for measurement of delta U, we use warm calorimeter. We use warm calorimeter. Okay? So warm calorimeter is used to find delta U. So what is warm calorimeter? So in warm calorimeter, there is a inner vessel which is called the worm. This vessel called as worm, and it is its covers are made of strong steel. Okay, this is made of strong steel. Okay, and it is fitted tightly to the vessel by means of metal lid and steel. Okay, so what actually happens in warm calorimeter is that in this a weight amount of a substance is taken in a platinum cup. Okay, so this is your cup. Okay, and this is your substance. Okay, okay. So you want to measure the delta, the change in internal energy of this substance. Okay, when this substance burns. Okay, so the combustion of the this substance will produce how much amount of heat you want to calculate. Now, this is connected with electrical wires for striking an arc instantly to kind of the combustion. Okay, so this is connected with these wires. Okay, this is your wire. What will it do? It will spark the heat, and which will lead to the ignition. Your substance will start burning. Okay, so the combustion will start, and what happens? The bomb, this whole cell is called as bomb. Okay, so this whole cell, this is your bomb. Okay, this is called as bomb, and it is then tightly closed and pressurized with excess oxygen. So for the burning of the substance, you need oxygen. Okay, for the combustion, we need oxygen. So supply oxygen is supplied from here. Okay, so this is the knob for oxygen supply. So once you move this knob in clockwise direction, your oxygen will supply from this, and it will go directly to your this bomb. Okay, so now the combustion will start. Okay, now this bomb is immersed then in water. Now this is your bomb. Now we will immerse this in water. See, we know the heat capacity of water. Okay? So if we know the heat capacity of water and the heat capacity of this calorimeter, the whole this whole setup is called as calorimeter. Okay? So if we know this, then we can easily calculate the delta U. Okay. The bomb is immersed in water in the inner volume of the calorimeter, and a stirrer is placed in the space between the wall of the calorimeter and the bomb. Okay. So now this is your water and this is a stirrer. So stirrer is used here in order to maintain the constant temperature throughout the calorimeter. Okay. So a stirrer is in the space between the wall of the calorimeter. This is your calorimeter. Okay. This whole setup is the calorimeter and the bomb. Okay. This was your bomb and this was your calorimeter. So that the water can be stirred uniformly. Okay. So water will be stirred uniformly over here and the temperature will remain constant throughout the system. Now, the reaction is started by striking the substance through electrical heating. This now the combustion will start by striking the substance through electrical heating. Okay. So now, uh, a known amount of combustible substance is burnt in oxygen in the bomb. Okay. Now you know the amount of the substance. Okay. The substance you are burning. Okay. In the presence of oxygen in the bomb, the heat evolved during the reaction will be absorbed by the calorimeter as well as the water in which the bomb is immersed. Okay. Now this is your substance burning. Okay. If 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 it burns, then it will what will happen? The heat will be evolved from the system. Okay. It will evolve heat. And what will happen if heat is evolved? Then it will be absorbed by your water and the calorimeter. And if it happens, then okay. So the change in temperature is measured using a thermometer. So here basically what we are doing, we are measuring the temperature difference using in the bomb calorimeter. So the temperature difference is thermometer. So this is your thermometer which is deep here in the water. Okay, so that you can measure the temperature. Now since the bomb is sealed, okay, this hole, okay, where is my phone? Okay. So this whole thing is sealed. Okay, this is sealed. Then its volume doesn't change and hence the heat measurements is equal to the heat of combustion at constant volume. Okay. See, here your volume is not changing, okay, because this is sealed. The volume is not changing. That means it remains constant. If this is the case, then your work done, which is nothing but minus of the dV, will be 0 because your dV is 0. Okay. Now, so if this is the case, then the heat measurement that is will be equal to the heat of combustion at constant volume, which is nothing but your delta U. So the amount of heat produced in the reaction is equal to the sum of the amount of heat absorbed by your calorimeter and the heat absorbed by the water. So if we take heat absorbed by calorimeter as Q1 and heat absorbed by your water as Q2, then what will happen? Your delta U will be equal to Q1 plus Q2. Q1 is heat absorbed by calorimeter and Q2 is heat absorbed by water. Then your delta U will be equal to the sum of both. Okay. So Q1, that is heat absorbed by calorimeter, is equal to K into delta of T, because it is proportional to the temperature difference. Okay, the heat of absorbed is directly proportional to the temperature difference. Similarly, okay, if heat absorbed by the water, which is Q2, your Q2, since we know the heat capacity of water, so it will be mW into Cw into temperature difference. This is what written over here. Okay, I have already told you here that your Q is equal to m into C into delta of T. So which is what written over here, where mW is molar mass of water in this case because we are using water, and Cw is molar heat capacity of water. Okay, so which we know already that it is 4184 kilojoule per Kelvin per mole. Okay, so now we have to calculate delta U, which is Q1 plus Q2. So let us put this value of Q1 and Q2. This Q1 and Q2 values in this equation, and putting this, we will get K into delta T plus M into C into delta T. Here delta T is common, so what will we do? We will take it out, and your delta U will become K plus MW, that is molar mass of water, into Cw, that is heat capacity of water, into delta of T. Okay? This is how you can calculate the change in internal energy. Okay? That is heat of combustion at constant volume. Okay. Now this calorimeter constant, that is K, can be determined by burning a known mass of standard sample. Let us say you know for the benzoic acid, the heat of combustion is known, which is minus 3227 kilojoule per mole. So if you know this, then you can easily calculate this calorimeter constant K. And the enthalpy of combustion at constant pressure of substance is calculated from the equation 7.17. Okay. So if we know this delta U, okay, that is enthalpy of combustion at heat, that is heat of combustion at constant volume. Okay. So your delta U is nothing but the heat of combustion at constant volume. And if you want to calculate the enthalpy of combustion at constant pressure, then what we will do? We know this relation, delta H equal to delta U plus delta mgRT. Okay. So what we will do? We will just write delta H. We will just put the value of this delta U, and then we will add delta mgRT. We can easily get the values of your delta H. Okay. It is nothing but delta U plus delta mg into RT. Okay. Now, what are the applications of this bomb calorimeter? So, bomb calorimeter is used to determine the amount of heat released in a combustion reaction. Okay, so we can easily calculate the amount of heat released, that is delta U, in a combustion reaction. Also, it is used to determine the calorific values of food. Okay. Next, it is used in many industries such as for they are used for metabolic studies, food processing, and explosive testing. Okay, these are the uses and application of the bomb calorimeter. So now you measure the delta U. So now how can you measure delta H? So in order to measure delta H, coffee cup calorimeter is used. Okay, delta H is what? Heat change at constant pressure. Here, this is atmospheric pressure, and it can be measured using a coffee cup calorimeter. So it is measured using a coffee cup calorimeter. So the its schematic representation is given here, and here instead of a bomb we use styrofoam cup. Okay, this is your styrofoam cup. Okay, so what happens? This is your styrofoam cup. So it acts as a good adiabatic wall and does not allow the transfer of heat produced during the reaction to its surroundings. Once a second. Yes. So this is your styro cup and it acts as a good adiabatic wall. So your adiabatic wall, what it did? It doesn't allow the transfer of heat produced during the reaction to its surrounding. So and this it, if the heat is not getting uh, transferred to the surrounding, then what happens? It will be absorbed totally by the water inside the cup. Okay, it will be absorbed totally by the water inside the cup, and then we can easily measure the delta H. Okay, so this method can be used for the reaction when there is no appreciable change in volume. Okay, so this is how we can measure the delta H. So here thermometer is used to measure the temperature. The same setup as the bomb calorimeter, the stirrer, and this is your reaction mixture, and this is your insulated stopper. Okay, so this is what how we measure delta H. Okay, now if we measure the change in temperature of water, and then we will use it to calculate the amount of heat that has been absorbed or evolved in the reaction using the following expression. So this was the expression initially also. Okay. So if the reaction is exothermic, the heat will be evolved in an exothermic reaction. Heat is evolved. If heat is evolved, that means your system will lose heat to the surrounding. If that is the case, your QP will be negative. QP will be negative. Okay. And if your QP is negative, that is heat evolved at constant pressure, then your delta H, that is enthalpy of the reaction, will also be negative. This implies so delta H R will also be negative. Okay. Similarly, for an endothermic reaction, if your reaction is endothermic, then heat will be absorbed by the system. What? Heat will be absorbed. And if that is the case, your QP will be positive. And if your QP is positive, then your delta H will also be positive. Okay. So here MW is the molar of mass of water as studied earlier, and CW is the molar heat capacity of water. Okay, and this is its value. So this is how we can measure delta U using a bomb calorimeter and delta H using a coffee cup calorimeter. Okay, and this was the equation we can easily use to calculate. Okay, now let us solve a problem. So here it is given that calculate the enthalpy of combustion of ethylene at 300 Kelvin temperature. temperature at constant pressure. So if its heat of combustion at constant volume, that is delta U, is minus 1406 kilojoule, the complete ethylene combustion reaction can be written as. Okay. Now let us quickly solve this question. So let us write the reaction for the combustion of ethylene, which is ethylene is your C2H4, which is your gas, plus 3O2 gas, and combustion produces your carbon dioxide gas and water. Okay, now what is given? We have given with delta U, which is equal to minus 1406 kilojoule. Temperature is given, which is 300 Kelvin, and we are asked to calculate the enthalpy of combustion at constant pressure. Enthalpy of combustion at constant pressure is nothing but your delta H, enthalpy of combustion at constant pressure, is equal to your delta H, and we know that delta H is equal to delta U plus delta of Ng into RT. Okay. If this is the case, we know delta U, we know R, which is a gas constant, and temperature is already given, that is 300 Kelvin. So now we have to calculate this delta Ng value. Now delta Ng, which will be equal to number of moles of gases in final minus number of moles of gases initially. Okay. So initial number of moles of gases will be subtracted from the final number of moles of gases. Okay. So number of moles of gases in this case, what is it? It is 2 only. Okay. We will not take this 2 because it is for liquid. We want to calculate only for the gases. So it is 2 minus of initial number of moles of gases. Okay, so it is 1 over here for gas, and oxygen is also gas, so we will also take this 3, 1 plus 3. Okay, sum of number of moles. So if you solve this, you will get 2 minus 2. This will be equal to minus of 2. So your delta Ng you get as minus of 2. Now let us calculate delta, which is delta U plus delta Ng of RT. Delta U is minus 1406 kilojoule. Delta Ng is your minus 2. R is 8.314 joule per Kelvin per mole. Joule per Kelvin per mole. And your T is 300 Kelvin. Okay. Now let us solve it over here. Minus 1004. Once again. So it is minus 1406 kilojoule. So here kilojoule is given, and here it is in joule. So let us, in order to convert your joule into kilojoule, what we do? We multiply it with 10 to the power minus 3. So let us do this. Minus 2 into 8.314 into 10 to the power minus 3. Now it will become kilojoule per Kelvin per mole. Okay. And it is multiplied with 300 Kelvin. Now we can add it minus 1406 kilojoule, and this plus and minus will become minus 2 into, now the whole thing is in kilojoule. Now we can easily add it. So it will become 2 into 8.314 into 300 into 10 to the power minus. Okay. It will become minus 1406 kilojoule. This is also in kilojoule. So minus 2 4 are 8, 2 1 are 2, 2 3 are 6, and 2 8 are 6 into 3. And we can write this 300 as 3 into 10 to the power 2. Okay. This 300, you can write it 3 into 10 to the power 2. And here we have 10 to the power minus 3. So if you have 10 to the power 2 into 10 to the power minus 3, what will it become? 10 to the power. If base is same, then we can add. Then if you add 2 and minus 3, it will become 10 to the power minus 1. Okay. So 3 into 10 to the power minus 1 will be nothing but equal to 0.3. Like dividing 3 by 10 is nothing but 0.3. So we will write it over this whole term 300 into 10 to the power minus 3 as 0.3. It will be 0.3. Okay, now if you solve this, you will get minus of minus minus. You will add, first you will multiply this and then you will add this to minus 1406 and you will get answer again minus. Okay, minus 1410.9 kilo. So if you solve this, you will get this. Okay, so this is what your value of, I will write answer over here. So this is what your value of delta H, which is equal to minus 1410.9 kilo. Okay. So what we have done here, we were asked to calculate delta H and delta U, and the temperature was given. So we already know this relationship between delta H and delta U. That is, delta H is equal to delta U plus delta NG of RT. We are given with the values of delta U and temperature, and we know the R is gas constant. So we were basically in this question we had to calculate this delta NG value. So in order to calculate delta NG, so this is very important. We have to take moles of only gaseous gaseous species. Okay. So that was the trick of this question. You have to take only the moles for the gaseous species. And so we after that we calculated the delta NG, and then we put substitute these values in this equation and solve it to get our final answer. Let us move to the next question. Here it is given that from the following data at constant volume for combustion of benzene, calculate the heat of this reaction at constant pressure. Here we have to do the same thing. Here delta U is given. So here in this case, your delta U is given, which is minus 3268.12 kilojoule, and it is given at temperature 25 degrees Celsius. Your temperature is 25 degrees Celsius, which means we convert this to Kelvin, it will become 298 Kelvin. So now we know the temperature, we know delta U. So now in order to calculate the heat of combustion, heat of this reaction at constant pressure. Okay, so we are asked to calculate delta H. Okay, so delta H is delta U plus delta NGRT. We know the temperature, we know the gas constant, and delta U is already given. So we have to calculate this delta N. Let us quickly calculate this. Delta NG is equal to the summation of number of moles in the forward reaction minus number of moles in the number of moles final condition, number of moles in initial. So this is your reaction. Okay, C6H6, which is in liquid state, 7 into 1 by 2. Oxygen, which is in gaseous state, and your carbon dioxide is in gaseous state. So in the product side, what is in gaseous state? Your carbon dioxide. So we will take the moles of this. So it will be 6 minus of here in reactant side, your gaseous species is oxygen and its moles are 7 into 1 by 2, which is nothing but 3.5. Okay, 7 into 1 by 2 is nothing but 3.5. So if you solve this, you will get 2.5. Okay, so your delta Ng here is 2.5. Okay. If this is the case, now let us quickly calculate your delta. So your delta H will become delta U is your minus 3268.12 kilojoule minus plus delta NGO is your 2.5. R is your 8.314. Okay, so we will, this is in joule per Kelvin per mole and your temperature is 298. Okay. So now your delta H will become minus 3258.12 kilojoule. So in order to add these values, so we will also have to convert this joule into kilojoule. So for that we will multiply it with 10 to the power minus 3. So it will become 2.5 into 8.314 into 10 to the power minus 3 into 298. So this whole value will become in kilojoule. Okay. Let us solve this. It is 3268.12 kilojoule plus your 2.5 into 8.314. If you multiply it, you will get 2.5 into 8.314. You will get 20.785. Okay, you will get 20.785. And we have to multiply it with 298 and 10 to the power minus. Okay. So your delta H will become minus 3268.12 kilojoule plus, if you multiply this 298 into 20.785, you will get 6193.93 into 10 to the power minus 3 is already here. So it will become minus 3268.12 kilojoule plus 10 to the, you can write this 6193.93 into 10 to the power minus 3 s. So if you want to write it, you can also write it 6.19393 into 10 to the power 3. Okay, we can write it like this because if you multiply this with 10 to the power 3, you will get this value. Okay, so we can write it like this, and here it is 10 to the power 3 into 10 to the power minus 3. So it will become 1. So we will be left with only with 6.1319393. Okay, so if we add 6.19393, okay, so this is plus minus. So plus minus we will have to do minus. Okay, so now if you minus this, you will get your delta H as equal to minus 36268.12 plus 6.1939. Okay, so if you do this, you will get your delta H as minus 3261.92 kilo joule. So if you solve this, you will get this value. Okay, so we have easily calculated the delta H, that is heat of this reaction at constant temperature. Okay, so this is what we have to do this in this question. Okay, so what are the applications? Okay, so now let us study the applications of the heat of combustion. The applications of the heat of combustion. It has application in the calculation of heat of formation. Since the heat of combustion of organic compounds can be determined with considerable ease, okay, you can easily calculate the heat of combustion of organic compounds. Okay, they are employed to calculate the heat of formation of other compounds. So here what they mean to say is that if you know the heat of combustion of compound, okay, then we can easily calculate the heat of formation of something. Okay? So here it is written that since the heat of combustion of organic compounds can be determined, they can be employed to calculate the heat of formation of other compounds. Okay, so if we know the heat of combustion, then we can calculate the heat of formation of the compound. For example, let us calculate the standard enthalpy of formation of methane. Okay, so in order to calculate the standard enthalpy of formation, what we need, if we know the heat of combustion of hydrogen, carbon, and methane, then we can easily calculate the enthalpy of formation of your methane. How? Let us see here. Okay, so here in this case, we have to calculate the enthalpy of formation of methane. Okay, from the values of the enthalpy of combustion of hydrogen, carbon, and methane, and these values are given to us. Okay, excuse me. So let us interpret the formation about enthalpy of formation by writing out the equation. It is important to know that the standard enthalpy of formation of pure elemental gases and elements is assumed to be 0. So I have already told you in your third or fourth class that your standard enthalpy of formation of pure element gases and elements would be 0. Okay, and also for your hydrogen, nitrogen, diatomic gases equals 0. Okay, so this you must remember. So the thermochemical equation for the formation of methane from its constituent element is. Now let us write the thermochemical equation for the formation of methane from its constituent element. Okay. So it is, we have to form methane. Okay. So what we will do, we will take carbon and hydrogen. So methane is CH4. So what we need, carbon and hydrogen. So carbon, graphite from plus hydrogen. The gases from will give you methane gas. Okay, so this is what the enthalpy of formation of your methane gas. So let us take the enthalpy of formation of your methane gas. Standard enthalpy of formation of your methane gas is X kilojoule per mole. Okay. Now we have to calculate the enthalpy of formation from the given values of the enthalpy of combustion of your hydrogen, carbon, and methane. Now let us quickly write the equations for the combustion of hydrogen, and then the combustion of carbon, and then the combustion of your methane. For the combustion of hydrogen, combustion of hydrogen, the equation for that will be hydrogen gas will be burned in the presence of half moles of oxygen, which is also gas, and it will produce water. Okay, so on combustion, it will produce water. Next, let us write the combustion of carbon. So, C graphite plus oxygen, and it will produce carbon dioxide gas. Next, let us write combustion of methane. So, what it is? CH4 plus O2. CH4 is your gas, oxygen is also your gas, and it will give out carbon dioxide gas and 2 moles of water, that is in liquid. Okay. So this is the equation of combustion for your hydrogen, carbon, and methane. And these values are given to us already. Okay. The heat of combustion is already given to us, which is for hydrogen it is minus 285.8 kilojoule per mole. So let us just wait for a few seconds. Okay. For hydrogen it is minus 285 0.8 kilojoule per mole. Okay, and for carbon it is minus 393.5 kilojoule per mole, and heat of combustion for your methane was given as here. For this was for hydrogen, this was for carbon, and this is for your methane, which is minus 890.4 kilojoule. Minus 890.4 kilojoule per mole. Okay. Now, if you want the heat of formation for this reaction, now we have to arrange this equation. Let's say we write this equation as 1, 2, 3, and 4. Now we have to arrange all these 3 equations such that we end up getting the equation 1. Okay. So what we will do? Let us start arranging it. Okay. So we want C on the left side. Okay. So C on the left side. So we will just add equation 3. We will take equation 3, and then we want hydrogen, but here 2 moles of hydrogen. So here in combustion of hydrogen equation, we have hydrogens in the left side. Okay. So now if we have hydrogen in the left side, but here it is 1 mole. So in order to have 2 moles, we will multiply this equation by 2, plus we will add equation 2 by multiplying it with 2. Next, what we will do? Okay. We also want, so in order to get your CH4 on your right side, here methane is on your left side. So in order to get in on right side, we will just reverse the reaction. And you know, if you reverse the reaction, your delta H will also get, its sign will get changed. Okay, its magnitude will remain same, but its sign will get changed. Okay, so let us reverse this equation 4. What we will get? CO2 gas plus 2H2O liquid will give CH4 gas plus 2O2 gas. Okay, and your delta H will now become plus of 890.4 kilojoule per mole. Let us name this equation as 5. Okay, so now we have, in order to get the equation 1, what we will do? We are adding equation 3 and we are multiplying equation 2 with 2 in order to get 2 moles of hydrogen, and then we will add equation 5 to it in order to get CH4, that is methane, on the right side. Okay, so let us do this. Let us add 3. 3 is your 3 is your S2. Okay, now I would not write all these things. 3 would be your H2. Sorry, 3 is your C graphite plus O2 plus twice of your, okay, twice of your this. This is your left hand side. Okay, this is your left hand side equation I am writing over here. After that I will write the right hand side. Okay, so this will become C graphite plus oxygen, then 2 into equation 2. So it will become 2 of S2 plus multiplying 2 over here, it will cut out and cancel out and it will become O2. And equation 5. Equation 5 is nothing but your CO2 plus 2H2O. This is your left hand side, and your right hand side is 3, equation 3, which is your CO2 on right hand side, plus 2 into equation 2, which is 2H2O, plus equation 5. Equation 5 is your here, which is CH4 plus twice of. Now here O2 and O2, it is 2O2, O2 and O2, it will become 2O2, and here on right hand side we have 2O2, so they will get cancelled out. Okay, so let us cut this O2 and this 2O2 will get cancelled out. Next, we have 2 moles of water over in left hand side and 2 moles of water in right hand side. It will also be cancelled out. Here we have carbon dioxide on the left hand side and carbon dioxide on the right hand side. Okay, so it will also get cancelled out, and what will be left with? C graphite plus 2 of hydrogen gas is CH2 gas. Okay, so which is nothing but your equation 1. Okay, so what we have done, in order to get equation 1, we have just done this. So if you are doing this, then what will happen to enthalpy? So we can easily calculate enthalpy of for the reaction 1 by using this equation. So enthalpy of formation for this reaction will become enthalpy of formation of reaction 3 plus enthalpy of combustion, sorry, in this case it will be combustion, 2 into enthalpy of combustion of your equation 2 and 1 into enthalpy of combustion of your equation 5. Okay, so your enthalpy of combustion of equation 3 is minus 393.5 kilojoule per mole. Okay, and plus 2 into enthalpy of combustion of equation 2 is minus 285.8. Next, we have enthalpy of combustion of equation 5, which is 890.4 kilojoule per mole. Okay, kilojoule per mole. So if you solve this, you will get the enthalpy of formation of methane as minus 74.7 kilo. Okay, so the enthalpy of formation of your methane will become minus 74.7 kilojoule per mole. This is your 7. Okay, 74.7. Okay. So this is the amount of energy that is required for the formation of 1 mole of methane, which is nothing but minus 74.7 kilojoule. If this is the case, then the heat of formation of methane will be equal to minus 74.7 kilojoule per mole. So the heat of formation of methane, the heat of formation of methane is equal to minus 74.7 kilojoule per mole. Okay, so delta H of HF of methane is equal to minus 74.7 kilojoule per mole. Okay, so this is your answer. Okay, so what we have done in this case, we were given the heat of combustion values of hydrogen, carbon and methane, and what we have calculated, the heat of formation. So this is the application of heat of combustion, where we can easily calculate the heat of formation using the values of the heat of combustion. If we know the heat of combustion of this compound, which is required for the heat of formation of that particular compound. Okay, so this is what we have done in this case. Okay, so this is okay. So in this class, what we have studied how to measure delta U and delta H using calorimetry, and if we then we studied that we use bomb calorimeter for the measurement of delta U, and then we studied what is the principle of the bomb calorimeter, what we do, and what is the equation here that is used in order to calculate the delta U. And after that, we studied the applications. Then we studied that the delta H can be measured using a coffee cup calorimeter, and this was the equation which can be used to calculate it. After that, we solved these problems, and then we studied the application of this heat of combustion. Okay, so what we studied here, that how we can calculate the heat of combustion using the heat of combustion value. So this is all for this class. Okay, so in next class, what we will study, we will study uh, the the application of the heat of combustion values in other cases. Okay, so this we will study in next class. Okay, so now I am ending this session.